Welcome to this video on linear algebra for GATE DA. Today, we'll focus on the concept of vector space, presented by Professor Manish. So what exactly is a vector space? It is a collection of objects, known as vectors, where you can add two vectors and multiply a vector by a scalar, all while satisfying certain rules. The simple idea is that if a set behaves nicely under both addition and scalar multiplication, it is considered a vector space. Mathematically, a set of vectors V with scalars from a field F is a vector space if vector addition and scalar multiplication exist and satisfy certain properties. Let's explore the properties, starting with the addition properties. These include closure, meaning the sum of two vectors is in V, and commutativity, where the order of addition does not matter. Continuing with addition properties, we have associativity. Also, a zero vector must exist in V, such that adding it to any vector V results in V. The fifth property is that an additive inverse must exist for every vector. For any vector V, there must be a negative V such that their sum equals the zero vector. Next, we examine the scalar multiplication properties. These include closure, where a scalar times a vector is in V, and associativity for scalars and vectors. The final scalar multiplication properties are identity, where 1 times V equals V. Additionally, two forms of distributivity must hold, over vectors and over scalars. Let's look at examples of vector spaces. The real space R squared is a vector space, as vectors can be added and multiplied by a scalar, and the results are still within R squared. Another example is the polynomial space. All polynomials, such as this example expression, also form a vector space. Specifically, all polynomials with a degree less than or equal to 2, including the zero polynomial and being closed under addition, form a vector space. Finally, the set of all 2 by 2 matrices forms a vector space, as matrix addition and scalar multiplication satisfy the necessary properties. Now, an example of what is not a vector space, the set of positive real numbers only. Since V must be greater than 0, the additive inverse, negative V, is less than 0 and not in the set. Consider the set of all polynomials of degree exactly 2. Example elements are shown, where the degree must be exactly 2. This set is not a vector space. To be a vector space, it must satisfy closure under addition and must contain the zero vector. Thanks for watching this video on vector spaces. Thanks and regards.